My name is Michał Chodzikiewicz and I am an embedded software engineer. I work at Taumatek, our host. And I have prepared for you a presentation about RTIC, which is, if you are coming from an embedded space, you might be familiar with real-time operating systems, so RTOS for short. And this is something that is kinda RTOS-ish, but has a bit different paradigm than, for example, FreeRTOS, which is most popular in the space, I guess. Okay. Okay, so not only about RTOS, there will be some additional tools which we will use to develop our, let's say, real-time application for an ARM microcontroller. So, ARM Cortex-M is a microcontroller architecture that is very popular, comes in many varieties. I mean, you can buy very small ARM Cortex-M0, for example, which will have just a couple kilobytes of flash and RAM. But you can also buy very similar regarding the architecture processor, like, for example, ARM Cortex-M7, which will have more than, I don't know, like 2 megabytes of RAM and of flash and maybe megabyte of RAM or something like this. You know, the range of the microcontrollers based on this architecture is very large. It also includes very different sets of peripherals, so you can use it for many different things. What is maybe not unique, but kind of important in ARM world is that ARM processors are produced by many vendors. So ARM is only licensing the architecture, the IP. So, and then vendors can buy this intellectual property and use it to build their own ARM Cortex-M microcontrollers. Because of popularity of ARM, there are lots of open source tooling and cheap hardware in the market. For example, you can buy very basic ARM-based development kits for, I don't know, like $5 even, or $10. And you know, the bigger the board, the more feature rich it will get. Let's say more expensive, but the starting point is very cheap. What is specific also for the Cortex-M architecture that divides it from ARM Cortex physical memory address space, and we do not have virtual memory, which is in our computers that we use on a daily basis is used to isolate the processes, for example. So this is something that we do not have, and for example, some part of your code might erase memory, or I mean override memory of different piece of code, for example. So it's more dangerous than just developing an ordinary PC application. Yeah, what is also characteristic for ARMs is that they are can be very low power. So they can juice up, for example, the very small battery like the one you use in watches. They could use it for a few years, for example, and operate, you know, doing some simple tasks every now and then. Okay, the microcontroller that we will use today is kind of a big beast because it has 216 megahertz, so it is quite fast for the processor that you write on bare metal and not using some kind of Linux or something like this, so no MMU. It has 1 megabyte of flash memory, has 320 kilobytes of RAM. It also has a floating point unit. If you need to do some signal processing, it might be very helpful. However, we will not use this today. It has SDRAM controller, so if your 320 kilobytes, which is on its own quite big, is still not enough, you can extend it by adding SDRAM. The SDRAM is like, you know, the RAM that was used on old PCs, like, I don't know, 15 years ago, I guess, or something, or even
before DDR.
Yeah, before DDR. Yeah.
Okay.
But these are
years ago or so.
Maybe, yeah. But they are still produced and used in plenty of embedded devices because they are cheaper to produce and easier to control than DDR. It also has LCD controller, so it allows you to display something on bigger screens without using any additional hardware, just connecting the LCD screen directly to your microcontroller. It also has, and this is very nice feature, some kind of primitive graphics accelerator. It's called DME2D.
GeForce 3050?
No, it's, you know, it's like the DMA. You know what is a DMA? It's direct memory access, I guess it stands for, and it is used to offload the processor when you simply need to copy memory from one place to another. So this is used to, you know, to copy all the data also in your PC. So the core does not need to be engaged to perform this kind of copy. It just offloads it to the DMA controller. And this kind of DMA is a bit specialized because it can, for example, during this copy, also convert between color encoding. So, for example, you could use, if you have LCD with 16 pins to address the pixel color on the LCD, you would normally use 565, for example, encoding, which means you have 5 bits for red color, 6 bits for green color. This is because the green is most for green, human eyes is most sensitive, so therefore you have this extra bit of space to make it a bit better, and then you have last 5 bits for the blue. But for example, it might be better for you to store the data in 24 bits, and this would mean that you have 8 bits per each color. So you can use this DMA2D, for example, to copy the image that is in 565 or in, to the 24 bits depth, or the other way around, depending on what you want to do. It also can, for example, draw rectangles on the frame buffer, so it's not like the continuous memory copying, but it can be told to copy
patches? But
yeah, like the lines, the single lines on the frame buffer. So it will copy one strip of bytes of the data and then skip some part of it and repeat it on the next line. So because in memory it is continuous space, but on the screen it is like ordered into D. So yeah, and it can also I guess do plenty other things. I'm not sure though. It can move parts of the frame buffer almost for free, like you know. Anyway, it can do some simple graphic operations, not like an OpenGL or something like this, something more primitive, but still does the job because you don't need to engage the processor, the CPU to do it. It also has Ethernet controller, which is very nice. We won't use it today, and USB. So, for example, you can program it. I mean the USB on the physical level. Okay. This is just the STM32F7 is just like this part. You use it to place it on your own design, for example. So It has plenty of IOs because this is quite a big enclosure. This is not actually the one that is on the board, but anyway, it comes in different packages. Okay, let's move to the board that we will use, and this is STM32F7 Discovery kit. Discovery kits are famous for being kind of a cheap for the features. This one is not that cheap because it costs a little under 80 bucks, I guess, or euro or whatever, but it's this range, or 300 zlotys. But it is available. You can buy it and you can use it. It's just like ready-made device that you can use to write your application before you will have your target device developed. So you can work on the hardware and the software at the same time, because you have this evaluation board that you can test your software on, even though you don't have your target device yet. Okay, it is very well documented because this is this is designed to be help for the developer. So obviously the manufacturer, which is ST Microelectronics, they documented it so you can use it as a developer. This one also has Arduino Shield headers, so you can plug all the Arduino modules to it if you want to expand its capabilities. And what is very important, it has basically this is more about the MCU, so like this part, but it has embedded HAL implementation. This means that it can use all the abstractions that are used in the Rust embedded space, let's say. So this is a set of traits that allow you to interact with hardware in the abstracted manner. Yeah. So HAL stands for hardware abstraction layer, if I have not said it yet. Okay, why use Rust on embedded platforms? Why is it a good fit? First thing is that it compiles to native code, which is the only option for embedded devices, basically, especially at this low end. So where you do not have Linux, but you are running your application on its own, so without any operating system. It has no built-in runtime. So, for example, Go also compiles to the native binary, but the problem is that Go has its runtime that you cannot get rid of. It takes care, for example, for garbage collection and so on. But in Rust, since you have parole checker, this is sort of like compile time garbage collection. Rust produces memory safe code, so it is very important. It is very easy to get these mistakes in embedded devices, and it can be even more dangerous than on the user space software on the PC. Because, for example, you could write some wrong bytes to a peripheral that, for example, I don't know, controls some device that could harm you or anything like this. So having memory bugs get rid out of the application just by switching the language is on its own quite comprehensive rationale for this. But anyway, it has very powerful compile time abstractions. So for example, Patrick also have showed this a bit. So you cannot configure the pin in a wrong way. So for example, if you use the pin as GPIO output, you will not be able, for GPIO input, for example, you cannot use it as an output, which could possibly break your hardware in some cases. So that's nice to have this type checking control over your hardware, let's say, it's not to harm yourself. It has support for many architectures because LLVM has support for many architectures. There are some works on having GCC as a backend also with Rust. It would be nice because GCC supports even more platforms, but this is not out of the woods yet, I guess. As I said, it has this standardized API, which is embedded HAL. It is a set of traits for common peripherals that you are used to when you program a microcontroller. So you could use just the traits for specific peripheral to write your own device driver or something like this, and then move it to another microcontroller, and it will still be useful. This is a bit unlike in the C++ space, where you have plenty of different ecosystems which are not compatible, and most likely if you port to different platform, you need to rewrite much more code than using this common API. Okay, and also Cargo, which is a Rust build system, fits very well to this building binary that you will program into the MCU, because it has plenty of capabilities to, for example, prepare the linker script using build.rs. This is a nice feature, but I won't cover this today. Okay. One different view on why Rust on embedded platform is that there is very nice tooling, especially in the ARM space. Huge shout-outs to Nurlink RS. As far as I know, the name of this is the Nurlink is like, do you know what Nurlink is? By the way, it's when you have bare metal surface that you want to get a good grip on, you engrave some kind of lines and patterns to make it to have more friction on it, so you can grab it easily, easier than if you have the plain metal surface. So it's like to get a good grasp on bare metal devices. They created this set of tools they called Nurlink, so that's the joke, if anybody wondered. Because you often refer to the microcontroller application, like bare metal application, because you have no OS there. And they created great tools, especially regarding today's example, DFMT, or DFormat, FlipLink, and program. Let's jump into DFormat. DFormat adds to your application deferred formatting capability. What this means is that in normal application you use stdfmt. So, for example, print line macro is is part of it, but as Patrick showed, it is not accessible in embedded space. So you have different alternatives, but the problem is that if you want to format strings on the CPU and you just use it for, let's say, miscellaneous logging, not for the the real application part, just for you as a developer, it is quite heavyweight to have these strings, because it is slow and it can impact operation of your MCU, since this is a very constrained device, let's say, with low processing power. Just parsing the strings and sending them out to your debug probe might be time consuming, and yeah. So using DFMT, it's like okay. So when you build the application, you have the linker script, which creates the instructions how to link all the sections of your program. And what DFMT does, it uses custom linker script that creates a fake section that will not go to the MCU. I mean, it won't reside on the flash or anything. It will just be this dummy fake section that will be used to store all the DFMT strings. So it will never be on the microcontroller, but you can refer to these strings from your application. So if you send, let's say, a reference to given strings, the host side, so your PC that you are debugging your device on, will put this string from the from your binary, from your ELF file, to your terminal, and it will not take place on the microcontroller. So you do not longer need to one, copy the strings. Second, format this, let's say, formatting inputs. So, for example, if you want to display, like Patrick showed, some string with a number inside that will change during the runtime. Using DFMT macros, it will just send reference to the string, so the index to the string, and the parameters that we want to format them in. And this will be done on the host side, so it will be very cheap, and you can log almost everywhere, because this operation, unlike formatting on the target side, is not noticeable in most cases. So you do not no longer need to limit yourself in your debug information. So that's nice. And also it reduces the binary size. I mean the footprint of the DFMT compared to normal format code is like 10 times lower. So it's also nice to have this reduced binary size. The second thing is the flip link. So the problem is that standard layout of memory in the ARM Cortex-M is that you have PSS plus data. This means all your variables that are static and are used through because you don't have heap. Usually you don't use heap on the microcontrollers, or at least you don't use the global allocator. So most memory you will need throughout entire time of the program, you will just statically allocate. So it will land here, and the problem is that you have this stack that is used to you know what stack is, I guess. So all your function calls and so on goes here, and it will raise up depending on how many function calls you have called, let's say, on this stack. And the problem is that if the stack will grow too big, it will overwrite your static data, and this is no good because you might not notice it and just operate as before, but your data is not longer valid. So a better way to handle this behavior would be to just crash at this point and maybe send some debug information on what was on the stack when it crashed. So the flip link also does some linker script magic, which reorders the sections in a way that BSS plus data is here, the stack is here, and if the stack will grow to the point where there is no longer RAM, the MCU will throw the hard handler exception. In this way, you can either dump the stack trace or just reset the processor if this is the release build and it is the real device that you give your consumer, for example. Yeah, so it is better to reset in this case than to pretend that nothing happened and then do something possibly horrible. Yeah. The third thing is program, and the program is it's like cargo flash and some other utilities combined together. So at the end, it makes the behavior of your cargo project look like you are developing on the host. So like regular Linux application or something like this, because you just type cargo run and it will give you the debug logs. I mean, it will flash the processor and it will start the application, give you the debug logs, and so on. So other important components that are not part of NUR linker RS, but we are using for today's demo is STM32F7 HAL, and this is embedded HAL implementation for STM32F7. It implements all the necessary types for the peripherals, and it allows to configure it. yeah, the nice thing is that, for example, you cannot use the same hardware resources twice. So, for example, if you use pin PA0 once as a digital output, and then in different part of code you want to get control of it, using it, for example, as analog input, it won't allow you because the borrow checker. So this is nice. This is also the common error when developing embedded software. The other component is embedded graphics. So embedded graphics is a set of traits that gives you the portability between different screens. For example, you can have monochromatic screen, like Patrick showed earlier, and you can also have this big colorful display with much bigger resolution, and you can use the same graphic primitives and an API for both of the screens, and easily port your code between very different screens. So it consists basically of the draw target, which is an implementation of a display, and the drawable, which is sort of a thing that we want to draw on the display. It also provides some primitives like point, line, rectangle, circle, text, image, and so on. And now to the main dish. It is RTIC, which is sort of real-time operating scheduler, which is task-oriented. The point of it is that, okay, I will show this later when we get to the specific application that we want to build. But this is a task-oriented scheduler. It allows you to share resources between tasks in safe manner. It gives you task prioritization and allows you to pass messages between tasks. It guarantees that you do not have a deadlock because it has very nice primitives for shared access. And it supports every Cortex-M device because it is both the strong part and the weak part. It is very tightly bounded to the Cortex-M architecture because it uses NV, which is nested vector interrupt controller, to do all the scheduling. Yeah. So let's go to our demonstration application, and it is like one thing we want to do is draw one of two plots on the screen, depending on which one we choose in runtime, generate the square wave, and listen for commands on serial port. We need to do this all simultaneously, or at least make it appear simultaneously, because it is not, in fact. Yeah, so how do we do this? If we dig a bit deeper into the internals, we need to set up our clock domains. So the MCU has, each peripheral, or almost each peripheral, needs to be clocked in some way. So we have this base frequency of 216 megahertz, but not all the peripherals can operate with such a high frequency. So, for example, you might need to provide different clock sources. So, yeah, the internals of microcontrollers allow you to do this, but you need to configure this. You need to configure all your input-output pins for specific purpose. For example, for the SDRAM pins, for the LCD screen, and so on. Then you need to initialize SDRAM. We need this SDRAM because we are using quite a lot of memory to store the image that we are displaying on the screen. We need to initialize the LCD itself, so there are clock sources and so on. We need to initialize the serial port, which was already talked about a bit in the AVR world. Then, after initialization, we can start generate the square wave. We can handle the request for redrawing the plot, and we can handle the request for changing the frequency of the square wave. So this is just like ad hoc requirement for application, but it is not that very different from real world use cases sometimes. Yeah, okay. So what constraints do we have? This square wave is not generated by the PWM which is like the dedicated peripheral to do this kind of things, and we do this just to show, because sometimes you don't get this hardware acceleration for time critical stuff, and if you don't, then you need to guarantee your code to execute in predictable time points, let's say. So just to present the importance of task priorities, in this case we are not using PWM generator, but we are doing it by hand. And we want the signal to be stable. And to do this, we need to prioritize this square wave generation to the highest prior. And the UART, so the serial port communication, also needs to be handled very quickly, because in our application we have no buffering. So we need to handle the character before next character will come. So it's also quite time constraint. Yeah. I guess this is the end of the presentation. I mean the PowerPoint presentation, but this is just the beginning of the let's say reading the code.
You do use Emacs?
No. This is IntelliJ, okay, in presentation mode. So IntelliJ also does not hurt you when you do embedded development, and also does not give you that much of a benefit. But yeah. Anyway, let's read some code. So RTIC is designed in a way that you have no main function, because it is already handled by RTIC macros. So we don't have main, and no STD obviously, because this is not a full-blown operating system target, but just a bare metal device. There is a feature that I used, but this is not important. This is just an implementation detail. We use okay. This is an import from another file, and this file provides some things that are necessary to make this DFNT deferred formatting work. That gives some dependencies to the RTIC. For example, it also gives you the panic handler that is compatible with deferred formatting. So even panicking can be deferred, even though, yeah, it might not be that big of a deal. Yeah, and we have exit function that is basically just to annotate to the host application that the operation of application have handled. Okay, back to the main, or maybe not to main. Let me. Okay, so what do we have here? Is basically the declaration of RTIC application. It gives the hint to RTIC what device is used. So it's STM32F7 peripheral access crate. So this is like a lower level to the hull, embedded hull. And since this is quite tightly bound to the Cortex-M architecture, you need to give some hardware interrupts that you don't use in the application, because in most applications you don't use them all, to allow it to schedule different tasks with different priorities. So CAN1 TX is most likely used for the priority number 2, and CAN RX0 is for number 3, for example. So the 2 is less important and 3 is more important, and 1 is even less important, and 0 is idle. It's, by the way. What we also have here is we use SysTick. SysTick is like general purpose timer for every Cortex-M device. We use it to measure time, basically. And there are some imports here that are not that important. And then we have the struct, which is called shared and has this shared attribute. This means that every item that is in this struct will be used in more than one task. So it will generate some mutex accesses to it, and so on. So this way you indicate you will use this in more than one task. And what we have here is the square wave period and the shape we want to draw on the LCD screen. Basically the number of shape. Because we have two of them, so we can either choose the one or the other one. Then we have the local struct, which is resources for tasks that are only used within this one task. And it is important to differentiate this because this way it allows you to skip all the synchronization part, the mutexes and so on. And then we have init function. The init function is the first function that will be launched at the start of the system. We have this default formatting info init, but as I said, this init, this string literal does not reside on the flash of our target device, but is interpreted on the host. That's the detail. Yeah, and then we do all sorts of initialization regarding Cortex-M. This is not that important, especially if you are not familiar with Cortex-M, then you can just skip it for now. And then we use function peripherals init that we get a couple of peripherals from. And let's jump to this function because it is quite loaded. Yeah, so what it does is basically it configures the clocks, as I said. It takes control over all the GPIO, so general purpose input-output pins, which can be used to be any function that given pin supports. Then we take two of the pins, which is GPIO A9 and GPIO B7, to use it as transmitter and receiver for the serial. Then we create serial port, so it is like the UART Patrick showed, with baud rate 115,200. It's like the common speed for the transfer. We set the interrupt to listen on the serial port, and then we get pin for generating our square wave. Then, this is the interesting part, we get a lot of pins to initialize SDRAM because it uses a lot of pins because it is parallel bus to the memory. So all these pins are used for the SDRAM, and there is this fancy macro that just does the job for you. Then we initialize SDRAM using this memory controller, and we use ready-made device driver. So this specific SDRAM chip is already supported by the FMC crate, which is extension to the STM32F7 HAL. Then we use a lot of pins to drive our LCD, and we basically create a frame buffer in the SDRAM. We create these frame buffers. There is a little unsafe because you cannot avoid this in most embedded applications. At some points you need to convert the raw memory to some more fancy types. So yeah, this happens. Then we create a display. So configure the peripheral and pass the frame buffers to the LCD controller, and then we enable the display and return all the peripherals we will need in our application. Okay, so that's for the init. Sorry, it was a bit long, but it is quite a lot of hardware to be initialized. Then we have idle tasks that basically does nothing in our case, but we could do this something that is least time critical, and this is the only place in our application where we have infinite loop. So this is just like, when we have nothing to do, then we will execute the idle task for infinite time. Then we have the LCD redraw. Oh, I made some tests before, but this should be like this. Okay, so this is LCD redraw. This has the lowest priority as possible because the redraw takes couple, I mean, like, I don't know, 20 milliseconds, something like this. So it is quite a long time because our square wave can have 2 millisecond periods. So if our square wave generator was lower priority, then it would stop to operate for time of redrawing the screen. So here we are redrawing the screen. If you want to check how it looks, this is I use this display. I clear it. There is a little hack because the DMA transfers in the examples from the web, which I have obviously stolen, had some issues, so I needed to hack it up a bit with the hard-coded delay. Then we create a curve from data, so our plot points. This is because we take a set of points that we want to draw a plot from. So then we create the plot. This is shameless plug. This is like my crate, but it is not very mature. But you can check it. It's called embedded plots. However, you draw the plot on the display. So our plot is implementing the drawable. And our display, by the way, I can show this to you, implements embedded graphics draw target. So here is some initialization stuff, so it doesn't matter, but there is a draw target with the color space RGB 565, which I mentioned earlier. You have this draw pixel, so this is the function just to draw single pixel, and then you have draw rectangle. The draw rectangle uses this DMA to D, as I said before. You can also implement some other primitives if you have hardware acceleration for it, but these are opt-in. Basically, you can just implement draw pixel and skip the rest of the methods. And size, you need to implement the size of the screen so that you can get the resolution of your image. But beside the size, you just need the draw pixel. But if you want to speed up, increase your performance, you can implement all this other method. Just for an example, we have implemented rectangle. So rectangle is also used for the clear, because clear is just drawing a full screen rectangle with given color. Yeah. Okay. So this is an implementation of the draw target. The embedded plots gives you the plot. Single plot is implementation of a drawable, so we just draw drawable on the draw target. And then going to the next task is our square wave handler, so generator handler. So by the way, the init function also spawned two tasks. One task is to draw the initial plot, and the second is to start generating the square wave. Okay, so what this square wave PFM stands for pulse frequency modulation, because I was too lazy to do the pulse width modulation, and I just opted in for changing the frequency instead of duty cycle. But nevertheless, what we are doing is we take control of our pin we use to output the square wave. At the end, I will show you how the square wave looks if you cannot imagine, because I don't know, maybe you are not used to embedded topics. Then you get the PFM state, so the square wave state. So either it is low or high at any given moment. Oh, maybe we can show maybe we can show just quickly to give you some imagination how the square wave looks, and also okay, so here we have our device and it displays a plot, and here we have an oscilloscope which observes the pin we are generating the square wave on. So it looks basically like this. It just goes down and up and down and up in specific frequency. So this specific one has 50% duty cycle, so it spends the same amount of time on the low and on the high. Yeah, back to the code, maybe. So this is how it looks, and how it is implemented. Obviously, it matches the state. If the state is true, then it sets pin low and the state to false, and if the opposite, it does the opposite. And it responds itself after time that is a period of our signal, because we can alter the signal in runtime. I will show this to you soon. And the last task that we have, which is also high priority but not as high as this square wave, is the USART1 handler. This is interrupt. This is hardware interrupt. So the peripheral, so the hardware inside the chip, like the real transistors and so on, are laid out in a way that it can tell your MCU to stop what it have been doing and immediately handle the incoming data on the serial port. So this is like an interrupt in RTIC. It is wrapped in RTIC. So what it says, it says binds to USART1. And by the way, each task, because I have forgotten to mention this, in this macro, you define which resources are being used in this task. So from local structure, you use RX and TX, and from shared resources you use the shape and the period. So why do we need these resources? Because we are just handling single character. So if there is something to be read, we match our character. If this is A, we draw the shape 0, and if this is a B, we draw on the LCD screen. We draw the shape 1, and numbers from 1 to 9 gives you different periods. So it alters the period. The 1 means that the 1 millisecond low, 1 millisecond high, and the 9 means 9 milliseconds low and 9 milliseconds high. So you can change the frequency. And what it also does, it echoes back what you have wrote to the serial port. Yeah, that's basically it. Let's do the demo. So as I said, thanks to program, I can show this to you how it is configured in cargo config toml. So basically you can define the runner, and in this case we just use program -- chip and the specific chip that we are using. Yeah. So let's do cargo run. It said that it have flashed the program with success. Yeah, and right now we can use the serial port, which is the different device, because this gives you the output from this D format info, but this is like only if the debug probe is attached. But this serial port is a physical interface, and if we type something, as you can see, it echoes back, and we can use these numbers. Can you show now the oscilloscope? So if we zoom out, you can see that we can change the frequency of the square wave, And what we also can do is we can choose which plot is being displayed. So this is the plot 2 and this is a plot 1. So that's basically it. But what I want to show you is that, can you show the code? Is that if you reorder the priorities, so for example you put 3 in here in LCD redraw, because right now we had, there was no effect on the square wave. But if we reorder the priorities and reflash the board, then
so LCD redraw is
taking a long amount of time,
priority, right?
and now it has the highest priority, right? And if right now I wanted to redraw the plot, it affects the generation of this square wave signal. So, but you can easily just shift the priorities, and one of the most, maybe not most, but important part of real-time operating system applications is that you need to prioritize correctly your tasks, because otherwise it will not look like it all operates simultaneously, right?
I would say it's one of the features of the life that you need to prioritize your task.
Yeah. Because in let's say general computing, it is more common to use schedulers like schedule policies like round robin, for example. So you do not want to starve any process. But in case of this kind of applications, you can live with the task or process that starves, because it is less important than the things that have higher priority. So that's the different approach. Yeah, so that's basically this. To sum it up, the most important thing is that this wraps everything that runs on the microcontroller. It has shared resources, local resources. It has the init function. You can spawn the task at given time, like here, spawn after period. Oh, sorry. Sorry for this. So once again, the shared resources, the local resources, and then you can spawn the task after specific time, for example, but you can also add to the this I have not mentioned. You can the context is always the first parameter, but you can add other parameters to the function, and then if you call the task with the spawn, you can pass this argument as the first argument. Here it will be second, but yeah, it will where it was. Yeah, it will use this parameter. So this is kind of a way to pass the messages between tasks, because you are spawning this with specific argument. And as you can see, all the tasks beside the idle are in the run to completion approach rather than infinite loops, which is more common in free RTOS, for example. But here it is more like oriented for short tasks that you prioritize. What is also interesting here is that, as you can see, for the local resources, you don't need any synchronization primitives, but for the shared access, you need to lock your resource. So there is this mutex abstraction. So if you lock the resource, no other task will access this at the same time. So this gives you the guarantee that you will not have a race condition, and it is very restrictive in this case, because it's not like in the CLAND where you can opt in for mutex, but you can also forget about it. In this case, every resource you can use is constrained within this shared and local structs, and this is controlled by the borrow checker and so on. So you are basically you can basically be very confident that no race conditions will happen. Yeah, I think this is mostly it. Yeah, thank you for listening and watching. And yeah, so thanks for Taumatek for hosting us. And I hope that we will see each other soon. Or